Hello everyone, thank you for stopping by my poster. My name is Hao-Chen Chang, and I'm excited to present our work titled Hierarchical-aware Orthogonal Disentanglement Framework for Fine-Grained Skeleton-Based Action Recognition, or HiOD for short. This research is a collaboration between Sun Yat-sen University, Beijing University of Posts and Telecommunications, and the Academy of Military Sciences. Our work addresses one of the toughest challenges in skeleton-based action recognition: distinguishing fine-grained human actions that are visually very similar, like reading versus writing or waving versus brushing hair. Skeleton-based action recognition is becoming increasingly important for applications in human, computer interaction, sports understanding, and smart surveillance. Compared to RGB videos, skeleton data is more robust to changes in lighting and viewpoint. However, existing methods often struggle with fine-grained actions, where motion differences are subtle and interclass variations are small. One key issue is that coarse-grained features dominate the training process, making the network overlook subtle details critical for fine-grained distinctions. Additionally, actions often exhibit implicit hierarchical relationships. For instance, writing and reading share similar motion patterns and can be grouped under the same parent category. Our goal is to leverage this hierarchical structure to better disentangle coarse and fine-grained features and improve recognition of subtle human motions. We propose the Hierarchical-aware Orthogonal Disentanglement Framework, HiOD, which consists of two main components: granularity disentanglement (GRD) and hierarchical prototype contrastive learning (HiPCL). GRD uses spatial-temporal granularity-aware orthogonal bases to disentangle the features into coarse-grained and fine-grained subspaces. In both spatial and temporal dimensions, independent bases capture different semantic granularities. Coarse-grained bases extract broad motion patterns, while fine-grained bases focus on subtle joint dynamics. To allow information sharing between them, we introduce shared orthogonal bases that project both coarse and fine features into a unified semantic space, enabling cross-granularity interaction. In this way, the model uses complementary information. Coarse features provide overall context, while fine features refine subtle distinctions. IPCL further enhances feature separability using a contrastive learning scheme that respects the parent-child hierarchy of classes. Since most datasets don't explicitly provide hierarchies, we automatically discover them using k-means clustering on fine-grained features. We then create two kinds of prototypes: hard prototypes for discriminating between fine-grained classes and soft prototypes that capture shared semantics among related classes. We combine these with two losses: a standard hard prototype contrastive loss for fine-grained learning and a soft prototype weighted contrastive loss for coarse-level learning. This design ensures the model learns both global consistency and local discrimination. We validated our method on several major datasets, including the fine-grained FineGYM and FSD10, as well as the larger NTU RGB+D 6120 datasets. The results are compelling. As you can see on the poster, HiOD achieves state-of-the-art performance across the board. More importantly, on a subset of particularly confusing actions from NTU 60, which we call the hard set, our method shows a significant +39% improvement over strong baselines. This proves that HiOD excels exactly where it's needed most, in distinguishing subtle, fine-grained actions. Additionally, our qualitative results, such as TSNE visualizations, clearly show that HiOD produces more compact intraclass clusters and more distinct decision boundaries. To summarize, our HiOD framework disentangles skeleton features into coarse and fine levels using orthogonal bases, facilitates interaction between these two spaces via shared projection bases, and leverages hierarchical contrastive learning to guide both global and local representation learning. This approach effectively mitigates the dominance of coarse-grained features, enhances fine-grained discrimination, and reveals underlying class hierarchies automatically. In the future, we plan to leverage the powerful semantic understanding capabilities of large language models to further explore the hierarchical relationships of action categories from the perspective of label semantics. Thank you very much for your attention.